What we'd now like to do is look at a couple of examples on how to work inductor problems and review inductors briefly. So the inductor physically is typically a coil. The symbol for inductance is L, and the unit for inductance is henries. Okay, and inductors store energy in the form of a magnetic field. And the energy stored is 1/2 Li squared. The relationship between the inductor voltage and the inductor current is that V is L di dt. So once again, it's a derivative relationship. So notice if I is constant, then that derivative di dt is 0, meaning V of t is 0. So under DC conditions, meaning constant current, DC conditions, inductors look like shorts, like short circuits. Okay, furthermore, if we look at that derivative di dt, what this tells us is that I cannot change instantaneously. If it did, it would mean that this derivative would try to approach infinity. So the two caveats for inductors are, under DC conditions, inductors look like short circuits, and because we store energy in the form of a magnetic field and cannot release that energy instantly, the current I cannot change instantaneously. Mathematically, that's a result of the fact that the voltage is proportional to di dt. So these are going to be particularly important in the next unit where we talk about RL and RC circuits. This fact that you can't have the current change instantaneously. Okay, like the capacitor, we can invert this derivative equation by doing some rearranging. So we get di is 1 over L V dt, and if we now once again integrate both sides, I get the integral of, I get I, because that's a perfect derivative. So I get I of t, so I'm going from I at 0 to I at t, and here I'm going from time 0 to time t. Then I get I of t minus I at 0 is 1 over L integral of V dt plus I at 0. Sorry, not yet. Just get rid of that. Come back here. So I at t is 1 over L integral V dt plus I at 0. Okay, so very similar equation to what we had with the capacitor, only here we're differentiating the current and integrating the voltage. So that inductor, once again, will hold on to that magnetic field. It will not release that energy instantaneously. So when talking about both inductors and capacitors, we refer to the fact that energy can't be released instantaneously from inductors and capacitors. We call the fact that there's a transition while it releases its energy, we call that a transient effect. Hence, inductor and capacitor circuits are often referred to as transient circuits. Okay, inductors in series behave like resistors in series. So L equivalent is L1 plus L2. inductors in parallel behave like resistors in parallel. So if I have L1 and L2, then L equivalent is L1, L2 over L1 plus L2. And by the way, capacitors in parallel. So if I had two capacitors in parallel, remember capacitors combine in the opposite way from resistors. So if I had C1 and C2, and I wanted an equivalent parallel capacitor, this would just be the sum, C1 plus C2. And that has to do with the way the capacity value appears in the current voltage relationship. It multiplies voltage, not current. So if you want to write it like Ohm's law, where you have something times current, you end up having 1 over C, which means the series parallel combination for capacitors is inverted from what it is for resistors and inductors. Inductors, the L multiplies the derivative of the current, so it behaves in combination like resistance. Alrighty, so those are pretty much the equations of importance for capacitors and inductors. So let's look at some examples. Let's assume we have an inductor current. I of t is, let's practice with something slightly more complicated. So we'll use this equation here as my way to review you on the product rule of differentiation. And let's say L is 2 henries. Now, inductors are kind of like capacitors in that a henry is a very, very large inductance. It's not unheard of. So it's possible to actually obtain an inductor in the henry range. You are more likely to be in the millihenry and below. But it's not quite as uncommon as with the capacitor to have a larger value of inductance. Okay, so V on this inductor would be L di dt. So it would be 2 henries times the derivative of this equation. So remember, in the product rule, we'll go ahead and factor out the 2. You take the derivative of the first, which would be 1, times the second, and then you take the first times the derivative of the second, which just brings down a minus 1. So if I rearrange that, I get 4 times e to the minus t minus t e to the minus t. Okay, and that is in volts. Okay, and I could simplify a little bit further if you wanted to, for e to the minus t, 1 minus t. Okay, now let's say we'd like to find the energy that is stored. And let's go ahead and say that we want to find the energy stored at 2 seconds. So before we went ahead and we said E is 1/2 Li squared, and we plugged in I as a function of time, and that is not a bad idea, because then if you want it for different times, you can do that. So we've got 1/2 times 2. And then for my current, I want to plug in this. For a reason, this guy keeps switching around automatically these locations. So I'll plug in the current to t e to the minus t and square that. So out of this, I should get 4t squared e to the minus 2t. And then when I plug in at 2 seconds, I'll get 4 times 4 e to the minus 4, or 16 e to the minus 4. Okay, and once again, you can plug in that 2.67 value for for E, and get an actual number out of this. It's going to be fairly small. And also, once again, this energy is in joules. Okay. We can also work an inductor problem if we're given a current. So let's say we're given I of t, or sorry, if we're given a voltage. So let's say we're given an inductor voltage. V of t is, we'll keep this fairly simple again. Let's just make it 3t squared. Okay, so V of t is 3t squared. So I is 1 over L, and we'll keep our same inductor value. It was 2 henries. And what you got to have here is you've got to have a current at 0. We'll say that's half an amp. Okay, so now we have 1 over L integral of V of t dt from 0 to t plus I of 0. So plugging in 1/2 integral from 0 to t of 3t squared dt plus half an amp. And so when you do that integration, you get 3t cubed over 3, and then minus 0 for the 0 end, plus times 1/2 plus 1/2. So it's 3t cubed over 6, which once again reduces to 1/2. 1/2 t cubed plus 1/2. Okay, and that'll be in amps, and that's I of t. Okay, so that's pretty much the kinds of problems that you would encounter. So some simplification. So I of t, V of t. Let's say we're given I of t is e to the minus t over 2 for t greater than or equal to 0. Now I want to comment on this because typically in inductor and capacitor problems, because of the situation where you can have initial conditions and you can have stored energy, currents and voltages that are given for inductors and capacitors are typically specified in the problem to be for t greater than or equal to 0, or for t greater than 0. So you're going to see that really throughout this discussion of inductors and capacitors, as well as inductors and capacitors and circuits. Now let me put some values here. Let's do 4 henries, 4 henries, and actually let's do 4, 6, and 3. Okay. All right, so what I want is find V of t. So the equation V of t is L di dt can only be applied to one inductor at a time. So, and the current that I'm given is the current at this node here at the top. So what I need to do before I can find the voltage, which is the voltage between top and bottom node, is I need to reduce this inductor configuration to a single inductor. So if I first handle the ones in series, that's 10 henries, and this is 3 henries, and then I need to do 10 parallel 3, so that's 30 over 13, which is about 2.3. Okay, so 2.3 henries. And now I have a a single inductor for which I can calculate my inductor current and my inductor voltage. And in this case, the current was given, so V is L di dt. So that would be, where am I, 2.3 times minus 1/2 e to the